Morning, guys. So yesterday we introduced a really important setup for doing a unit conversion, especially when we're dealing with really large numbers or really small numbers here. We might actually need to use one of those metric prefixes, those powers of 10 here. We solve for unit conversions. We set them up as unitary rates. We multiply them off as fractions so that top unit cancels bottom unit, and they basically sort of cancel all the way along. So I'm going to give you a quick practice question there. I'm going to show you one other sort of complexity to that question. And then towards the end, I'm going to introduce to you just a little bit of work regarding graphing. So let's just practice here for a warm-up. So practicing through some unit conversions. I want you to convert for me, let's see, number one. How many hectoseconds in 1500 milliseconds? And two, I'm going to give you one that's sort of a fraction. So let's go, how many centigrams per liter in 2.4 grams per kiloliter. Right? So just do that for practice here. Let's just show our work. So question mark. I'm going to put the unit that I want to end off with. In this case here is hectoseconds on the left-hand side. If you're ever stuck, just start off with the number as given to you. So this one here is 1500 milliseconds. We're going to go through, this seems strange. Again, I'm going to start picking up a fraction here, multiply by a fraction. I'm going to go through just dealing with the units first. And just like we saw yesterday, what I really want to say here is I want to say, well, milliseconds is on top. I want to put milliseconds on the bottom to cancel out. What I want is I want to go hectoseconds on top, but I may not know, without the chart in front of me, how many steps are between milli and hecto. You do need to memorize these prefixes here. We saw the strategy from yesterday was the power of doing this unit cancellation method is you can go milli back to hours, back to the base unit first, and then once you have seconds, so milliseconds is cancelled, seconds is on top, you can get rid of the seconds as a ladder step, and then go to hectoseconds afterwards. Right? So you can tack on as many fractions one after the other, as long as the final unit that we have is the hectoseconds that we want. Now we need to go through and we need to find one true relationship between these guys here. In this case here, remember I said the easiest conversion factor is put a 1 beside the thing that's bigger. Which is bigger, a seconds or a millisecond? Well, seconds is bigger. Which is bigger, a hectosecond or second? A 1 on top there. By putting the units to cancel out here, this will guarantee that I multiply and divide appropriately here. And at this point here, if you look back on your chart, milli actually stood for 10 to the negative 3. It doesn't make sense if I put 10 to the negative 3 milliseconds, a really tiny number of a really tiny unit makes one big unit. Nope, that doesn't make sense. By putting a 1 beside the thing that's bigger, I've converted all the negative powers into positive powers. If they were positive powers, they just stay positive powers. But at least this one here avoids me to deal with negative powers. This basically says I need 1,000 thousandths of a second in order to get 1 full second. So in comparison here, we can have a hecto. Hecto on the chart from yesterday meant 100, so 10 to the 2. In this case here, this one was a positive power. 1 hectosecond is 10 to the positive 2 seconds. Fine. So I type this into the calculator here. Numbers on top you multiply. I wouldn't bother typing in times 1. It doesn't change anything. Divide out 1,000, divide out 100, and this gives me here 0.015. Make sure your final unit here has units, hectosecond. We'll come back in tomorrow's lesson to talk about rounding. Second question here, a little bit more challenging because this time, my number here, my unit actually has a fraction. Remember our strategy, in addition to the, well, we want question mark centigram per liter. This is sort of like a density here. Because I have a fraction of the unit, I want you to write out that fraction explicitly. The 2.4 goes with the top unit. 2.4 grams, when you say per kiloliter, what you mean is all over 1 kiloliter. And once you have it as a fraction, it's not as hard for you to track for yourself. Well, gram has to eventually get to centigram, and then kiloliter has to eventually get to liters. Doesn't matter which one you do, so let's just do the top one first here. Grams is on top, I don't want it anymore. Put grams on the bottom. Let's put, 2.4, yeah. I want to put the centigrams on top here. So you see top unit cancels bottom unit, and the only sort of real surprise here is because I have kiloliters, this is already on the denominator. To get rid of it, I need to put kiloliters up above, and I want liters on the bottom. So again, it's a little bit weird if it's the first time seeing this here. I'm going through, I'm just putting the units so that they cancel out. Top unit cancels bottom unit and all that. Let's go through and just punch in the conversions. Which is bigger, a gram or a centigram? Well, gram should be bigger. So 1 gram is actually 100 centigrams, just like 1 meter is 100 centimeters. Which is bigger, kiloliter or liter? Well, kiloliter is bigger, and this picks up here 1,000 liters. This one here, 2.4 times 100 divided by 1,000. This gives you here 0.24, and your final unit centigram per liter. It would have been sort of all over liter, and I just re-express it back into that fraction there. As we start doing unit conversion somewhere here, it's totally possible that sometimes, maybe I had 2.4 to begin with, it's possible I still end up with 2.4. That's just coincidence here. It just says maybe there's a certain combination of units that are actually essentially the same, but we still see from the conversion factors here, well, no, in this case here is actually off by a power of 10. Especially as numbers get to be really large, really fast, and really small, really fast. I just want to rehash with you scientific notation. So scientific notation, also called exponential form, is sort of using an exponent to, using this one here to express very small or very big numbers. And how this works here is the standard way of writing this one here, not the standard form. Okay, but the standard way of writing it here is going to be something like 1.2 times 10 to the 5. That is in scientific notation. That's an exponential form here. Essentially, the things I'm going to be looking out for is the first digit has to be between 1 and 9. They can come with any other number digits here. We'll talk about significant figures in the next lesson here. And what we've done is instead of dragging out a lot of powers of 10, we've actually separated off the order of magnitude. This one just puts you in the right position. This puts the decimal in the right orientation. So in this case here, because this is 10 to the positive 5 here, it's like taking the number 1.2. That order of magnitude here moves the decimal place 5 times. 1, 2, 3, 4, 5. And therefore, anything that I skipped over just a 0, I'm actually talking about the number 120,000. It's just a little bit more simply written. Sometimes you will see some sections will have 12 times 10 to the 4 or 0.12. Those aren't proper scientific notation because the first digit should always be between 1 and 2. Basically, I moved the decimal place so that that first digit worked out so nicely. Positive powers will make numbers bigger. You move the decimal place to the right. I can also use scientific notation to make things smaller. Let's say I have 4.6 times 10 to the negative 3. Right? Not overly tiny, but that's like taking this number here, 4.6. That's proper scientific notation because the first digit is between 1 and 9. And because this is a negative power, I'm actually going to move the decimal place to the left, this time 3 times. So 1, 2, 3. The decimal is sitting here. The ones that I would have skipped over here are 0. So this is actually the number 0.0046. So it's a tiny order of the magnitude. That's what the negative power means. We actually get smaller. We're actually dividing by powers of 10. Your calculator actually does this really well. Instead of in your calculator having to type in, which is totally okay, 4.6, you can go times 10 to the hat negative 3. Your calculator is so used to doing scientific notation, most calculators will actually shortcut this part for you here. And when it shortcuts it, it'll usually say here either it's a single button that says EE or an EXP, or even better yet here, it just tells you what operation it's doing. So all you would have to do is you would actually type in 4.6, you just press the EE or the EXP, and it already does this times 10 to the power of. It saves you a little bit of typing, and all you need to do is you need to type in the power afterwards. Not completely obvious right now, but basically one other advantage that it does by using this EXP is it actually automatically puts brackets around this. It keeps this number together. And therefore, later on, if I need to multiply or divide numbers like this, I won't need to worry about brackets becoming an issue. Sometimes your answers in your calculator, they actually give you the answer. Oh, the answer is 4.6 E negative 3. That's what that E means. If this was a quiz or a test, I'd still want you to write out that E is just sort of simplified shortcut notation. I still want you to write it out. Oh, that means 4.6 times 10 to the negative 3. Right? So you still write it in the proper exponential notation. You're going to find on the worksheet, it'll either ask you, what's the answer in scientific notation? Generally, I tell people, just use it when it's convenient for you. Right? So if the number isn't all that bad to look at, yeah, I can bear with the 0.0046, so be it, just leave it. If it's not in exponential form here, this is called standard form. your worksheets just give you practice, making sure you know how to do the conversion, but outside of the worksheet, you just use it when it's convenient. So that's what the EXP and the EE button are. Make sure you can find it on your calculator. One quick aside here, be careful. Let's imagine I type the number here 2 hat 3 versus 2, our new EXP 3. Are these the same? Well, let's see what this means here. 2 to the power 3 means 3 multiples of 2, right? 2 times itself, 2 times 2 times 2. Well, that would give you 8. This EXP, this EE also means to the power of 3, but this is actually telling you it's 10 to the power of 3. So what's actually happening is this is actually scientific notation. 2 times 10 to the 3, it's not the 2 that's being multiplied 3 multiples, but in this case here, it's actually being multiplied by 10 to the power of 3, so it's multiplied by 1,000. You see that these are actually different. So in some sense, both of them are taking the power, but it really depends on what's actually taking that power there. So just watch out for that button there. I know your graphing calculator has it as a shift, like you press second something, but you should be able to find the EE button as 10 to the and then you just type in the power. Let me do one last sort of technique with our unit conversion method, and then we're just going to do a quick overview of graphing. So the unit cancellation method here actually works if we actually deal with multiple dimensions as well. We're not going to need to do this last conversion all that much, but just for completeness sake, I just want to show it to you how it works. Let's say I'm interested in doing one more conversion here. I want you to find for me how many centimeters squared in 3 meters squared. So I just throw in another sort of layer of complexity here. We are still interested in converting units. I'm still interested in converting something like meters to something like centimeters. I've seen that before. But the new bit, this time it's not fractions in the unit. This time it's actually a power. If I draw a picture, hopefully this makes a little more sense here. 1 meter squared would be an area. If I measure 1 meter on both sides here, 1 meter squared is the area that's covered by this red box here. I happen to have 3 of these, and what I'm interested in is for you to do a conversion. I now have a smaller box here. This is just actually 1 centimeter on either side. The area covered by 1 centimeter square here is just a centimeter square here. I want to know if I have 3 of these red squares, how many of these blue squares would actually fit on the red? Unfortunately, if you think through the conversion that we know so far, we know 100 centimeters is a meter, right? I've done that before, but I don't know the relationship between centimeter squared and meter squared. So case in point here, if you try to do your conversion method here, I'm interested in my final unit being centimeters squared. How many of these blue squares? If I have 3 of these red squares, what I really want to say is I want to do, well, meters squared to cancel out, I want to go to centimeters squared. The problem's going to be you may or may not know how to do this conversion. Actually, for this one, you might know it, but I'm just going to show you a technique in case you didn't. So what we're going to do here is just something a little elegant here. If I put the centimeter square here on top of the grid here, how many blue squares can I fit to go across a row, right? Well, since this is going to be a meter across and a meter is going to be 100, I'm going to actually need to multiply by 100 to just get the row, right? Just line up 100 of these blue squares here to reach all the way across the red square here. However, this has just gotten me a row here. This one here has not covered the entire area. That's only covered one of the dimensions. How many rows of these would I need going the opposite way, so going upwards here, to actually cover the rest of the area here? Well, just like before, 1 centimeter on every side, it's going to be 100 centimeters, 100 squares. I need to multiply by 100 that way as well. So what you're seeing in this problem here is we're actually multiplying the 100, but we're doing that twice. We're actually using the one-dimensional conversion, but that same conversion 2 times. So instead of trying to pick your head around meter squared to centimeter squared, let's just try to go meters to centimeters, use the one-dimensional conversion, but use that one-dimensional conversion twice. Because what's going to happen here is a meter squared means meters times meters. The meter squared will get killed off by the meter times meter here. We'll pick up 1 centimeter here, pick up another centimeter here. That multiplied together will give you your centimeter squared. And that allows you to do the one-dimensional conversion. 1 meter is 100 centimeter. You multiply 100 once to get the row. You multiply 100 again to get the other side. So this ends up being 30,000 centimeters squared. You can sort of parallel that. If this was a cube, you just do that conversion 3 times. You can be super elegant here. You can actually write this out. Because I'm multiplying the same conversion twice, I can say, well, it is 100 centimeters over 1 meter, but that conversion all squared. So again, we're not going to have to do that conversion all that much. I think your worksheet may have one of those practice questions, but I just want to show you with this technique of canceling out units, setting up these unitary rates here, it can actually help you do a lot of unit conversions. What we're going to do here is we're going to switch over just to a little bit of graphing practice. I just want to introduce to you just some of the language that you've been used to seeing in a graph. What are the advantages of a graph here? I want to just make sure you're comfortable with the vocabulary, and then we'll go from there. So for a graph, definitely, what is a graph? A graph is a visual representation of data, right? Sometimes data comes to you as lists and lists of numbers here. It's not so easy to see trends. What a graph does is it actually plots it out as a picture so that you can actually make some observations more big scale. So let's imagine we were doing an experiment here, really simple experiment. Let's start off with just a scale. Our scale here is just going to read a certain number of grams, a certain number of mass, and all we're going to do is we're going to take some wooden blocks here, and we're going to just put the wooden block on there. Each of these wooden blocks here represents maybe 1 milliliter worth of space, and all I want to know here is I want to figure out here, for every milliliter of this block of this material, how many grams does it take? So what's going to happen here is I'm going to have a list of masses and volumes. In this case here, because it's totally up to me how many volume cubes I actually put on, my volume is actually going to be called your independent variable. So in this case here, let's say independent variable, just some nice terminology review here. Independent variable, this one here is the condition that you change. Okay? So this is you change or you manipulate this variable. So I can decide to put on 1 square or 2 squares or whatever. This one, independent variable. Our independent variable is usually going to be the x-axis, and in this case here, our independent variable was volume. Right? What we're actually measuring this time is we're actually measuring what does the scale say as I slowly put on more and more of these blocks here. The one that might change is going to now be called the dependent variable. It might depend on the changes that you're doing to volume. That's called your dependent variable. This one here is the one that might change. It's totally possible the two variables that I picked off, they actually don't have any relationship. It could be no relationship. That's why I'm just using the terminology here. It might change. It might respond. So the sort of wording here is it might respond. It might alter depending on what I did to the volume. The dependent variable is going to be the y, and in this case here is going to be your mass. And basically, so far, I can do this experiment. I can say, when I had no volume, I have no mass. When I have one volume, right, one of these cubes here, maybe it reads 2.1 gram. When I put 2 of these blocks on there, maybe it reads 4.0 grams. When I put 3 blocks on, let's say it reads 5.9 grams. Right? So my experiment is I slowly manipulate, I slowly change, I slowly put on more boxes, and I just want to see how the scale responds. This time, I definitely see a correlation. I've only taken a reading at 0, 1, 2, and 3. Could I have put 1.5 blocks on or 2.5 blocks on? Of course I could have. That's what actually graphs do better for you. So in this case here, if I plotted a graph, again, just sort of terminology for you here, we will always put our x, which is our independent variable, in this case here our volume, our independent variable, our volume on the x-axis. Our y is going to be our dependent variable. This is the one that might change. This one here is, in this case here, the mass. So if we were labeling this here, this one we might say mass measured in grams. On the other side here, we'd say volume measured in milliliters. All right? So again, we've only taken a reading at 0, 1, 2, and 3. Make sure when you scale this, everything is nicely evenly spaced. So I have 0 cubes, 1 cube, 2 cubes, 3 cube. I've only taken a reading at a few of these set numbers. The scale on the x doesn't need to match up with the scale on the y. So the scale on the y looks like I get up to about 6 or so. Let's make it maybe a little bit more narrow of a scale. 2, 4. You just need to give me a sense of the scale. You'll notice that this spacing here, 0 to 1 here, may be different from this spacing. That's totally okay. And basically all I've done here is I've put down a few coordinates on my graph. I want you to plot the coordinate 0, 0. So we have 0, 0 right there. We have 1, 2.1. So when x is 1 with 1 cube, the mass is actually 2.1. I have another point there. When a mass of 2, I have a volume of 4, so 2, should use a ruler for this here. For 3 cubes here, it's 5.9, 3, 5.9, right? And what you're noticing here is I'm actually getting a visual way of actually seeing this data. All right, so I got those numbers there. I definitely didn't do this really well to scale. Most of the graphs in high school are going to be straight lines. If it happens, so if my graph here, if it looks like it's curved, then draw a curve. In this case here, maybe I draw a straight line, maybe like that, just using a ruler. I just try to approximate it. Given any experiment we'll see in the next lesson, there's always going to be some errors that come into play. Sometimes a little bit high, sometimes a little bit low. I'm taking down many readings to try to minimize some of those problems there. So we have that line there. We call this line a line of best fit. Again, most times it is a straight line fit, but if it is a curve, just draw it as a curve. That's fine. So there's my best fit line. My graphs not only give me a picture way of seeing this here, my graphs actually help us interpolate. They help us track the pattern, and they help us say, what if instead of doing a whole cube, like 1 cube, 2 cube, 3 cubes like that, what if I put 1.5 cubes? Is that possible? Well, although I didn't actually get a reading at 1.5, if I just trace the pattern that's followed by these variables, the 1.5 here, I can sort of interpolate, I can sort of figure out how much mass a 1.5 cube would be. It's called interpolation when we're sort of inside. So if I interpolate, I'm sort of tracking the pattern inside the data set that I had. I had 0 to 3. I can predict the pattern inside. If I extrapolate, I basically have no other data afterwards. But if I pretend this trend here just continued onwards forever and ever, I can, to some extent, I can extrapolate beyond what we have. I can start saying, you didn't take a reading at 4 or a 5, but if, assuming the pattern continues, I can track what a 4 is likely going to be, I can track what a 5 is likely going to be, as well as all those in-betweens there. Make sure when you do a graph here, yes, definitely you have your labels, right? Mass in grams, this one is volume in milliliters. Usually we want to title the graph. The title of the graph will typically be y versus x. In this case here, y variable, my dependent variable is mass. So I'm going to say mass versus volume. So we're starting to see sort of a graph as a nice visual representation. It's nicer to look at than, let's say, tables and tables of numbers. And it actually gives us the ability to track patterns. It helps us track which points may be somewhat on the high side, somewhat on the low side. Maybe I had a point here which is sort of way off the pattern. Maybe I'm going to call that point here an outlier. This point here just lies so far out from the pattern, I'm just going to ignore it. Maybe I totally misread that number there, right? So the graphs give you that visual representation. For a fair science test, you should always only have one independent variable and one dependent variable. The reason for that is I want to see the relationship between, in this case here, if I change volume, does the mass change? If I see any difference in mass, I want it to be associated to be the variable that I changed. If there are many conditions that change, if the temperature is fluctuating, if the pressure, the light intensity in the room is fluctuating, changing, sure, I might see a change in the mass here, but I wouldn't be able to associate, no, it's because of the volume that was affecting the mass. That's why for a fair test, we want one of each. And in fact, we want to keep all the other variables constant. We're going to call all those other variables controlled variables. Yes, sometimes people say, oh, use the same equipment, right? Don't switch scales, right? Don't use balance number 1, and then when you do the 2 boxes, do a different scale, because every scale is calibrated differently here. Yes, using equipment is a good idea, but in terms of control variables, I'm thinking of keeping other environmental conditions constant. So control variables keep everything else. So everything aside from volume and mass in this case, keep everything else constant. And some variables I'm thinking of here could be, let's say, the room temperature, right? Make sure it's not fluctuating really crazily, the room pressure, or the light intensity. Now, you might say here, in this experiment, what does light have to do with anything, right? What does light have to do with the size of the block? It may have nothing to do with it, but I just want to make sure I don't do one in a bright room, one in the dark room, so that if I see the mass change, I know it's because of volume and not because of light intensity. So I want to keep everything else controlled. In biology, you just actually call an experimental condition control, and basically that's the standard and that's the reference that I sort of compare it off of. Right? I'm going to show you just one last little neat trick I can do with graphs. Let's say I was doing an experiment here. I'm going to have a balloon. This balloon here is going to be filled with a certain amount of gas. And what I'm interested in is I'm interested in taking a reading I'm going to slowly squeeze this balloon. I'm going to apply a pressure. And what I'm interested in here is, how does my volume respond, right? What is the size of the balloon, assuming the balloon doesn't pop? Now, in general, when we deal with our ideal gas law, we know as I increase the pressure as you squeeze this balloon, I'm going to assume that the temperature is constant. I don't want that to fluctuate, light intensity, humidity. I want to keep all those other ones constant. But I would imagine, I have a hypothesis that if I increase the pressure, I would expect the volume to actually decrease, right? In this case here, they say pressure, better spelling here, pressure and volume are inversely related. They are oppositely related. When one gets big, the other gets small. Right? Graphically here, if I did this experiment, right, I'm actually going to plot pressure on the y-axis, volume on the x-axis, just so that I can make a comparison later on here. Based on this inverse relationship, I would expect when I squeeze this balloon really, really tightly, right, really, really high pressures, the volume would be really small. So as I go higher and higher on this pressure chart here, I would expect the volume to be smaller and smaller. The balloon is not all that big. But what would happen if the balloon here started expanding? It's because the pressure is actually dropped. I would actually end up getting, let's say at high volumes, a big amount of space. It's because the pressure was low. Just to introduce to you, well, sometimes here it's not always going to be a nice straight line fit. This one here actually follows more of a curve fit. We are calling that one here an inverse relationship. Mathematically, though, if you're familiar with the shape graph, we're actually representing, this is actually a reciprocal function. Pressure is actually proportional. Some constant K depends on how many particles, what temperature I'm actually at, even though it's staying constant here, but it's proportional to 1 over volume. It's not impossible to actually fit to this graph here. So imagine having a set of data. You have a bunch of volume readings, a bunch of pressure readings, and that's actually what's giving you this graph here. Some of them are still high, some of them are still low, but it's giving you a best fit curve here. What I want to do is I want to see if I can somehow manipulate the way I'm plotting the data so I actually get it as a straight line. What I'm introducing here is a notion of something called linearizing the graph. I don't really want to fit to this reciprocal. Make a note of that one there. This is called the reciprocal function. I don't want to actually try to fit to a curve because that's a little bit harder. What I can do is I can actually linearize the graph. I can force the data to be linear. And this doesn't mean coming in and actually changing the numbers, changing it from what it actually is. All it is I'm going to manipulate, instead of plotting pressure against volume, the part that was problematic in this setup here is actually this 1 over volume part. Because there is a 1 over volume, that's actually giving me this sort of curve relationship. What if, instead of plotting pressure against volume, what if I called this variable a? What if I let a equals 1 over volume? And therefore my function ended up becoming, let's plot pressure proportional through a. So what's happened here is by redefining a new variable, by hiding this ugliness of the fraction, I now have a much easier relationship. Now I have y and x here. Now it is just a straight line fit. It's just going to have a slope of k, and that's just going to be mx plus b. It's going to be a straight line. I haven't actually fudged my data, fudged my numbers. All I'm doing is I'm playing around with how I'm plotting it. What I'm going to do here is I'm going to take my set of data. Instead of just treating it as volume against pressure, which was problematic, I'm actually going to calculate a bunch of these 1 over volume readings. So imagine taking this reading here. Let's say my volumes, quite simply, let's say they go from 1, 2, 3, 4, 5, right? They had corresponding pressures to go along with each of these numbers. Instead of plotting pressure directly against the actual space, I'm actually going to plot it against 1 over volume. So I do a little bit of math. 1 over 1 is 1, 1 over 2 is 0.5, 1 over 3 is 0.33, 1 over 4 is 0.25, 1 over 5 is 0.2, right? So I've taken the data set here. Sure, I've re-expressed them. I haven't made up any numbers. But what I'm going to do here is I've actually hid that ugliness. I've hid that fraction relationship. I'm going to keep the pressure the same because my formula says pressure should be proportional to this new unit. And basically what I'm going to end up having here is if I plot those very same pressures again, but this time pressure against 1 over volume, now I have a 1, a 0.5, a 0.33 somewhere along the way, right? 0.25, right? I just want to make sure that my overall scale is actually even. What's going to end up happening is I hid the ugliness that would have actually given you a curve, and this part here will actually end up giving you a nicer straight line, which you can do a best fit to it. If it's a straight line, I can do a y is mx plus b sort of fit. So even in the case when a best fit doesn't come out as a straight line, I can play around with how to actually plot the data. Right? Sure, I may need to do some manipulations, in this case to take the reciprocal of all the volumes before I actually do the pressure again. But when I plot pressure against this 1 over volume, it comes out as a straight line. It's much easier to fit to. You can then read values again. Oh, I didn't take a reading at 0.75. You can still read the pressure reading here. This one here would be the 1 over V reading at 0.75. If you really wanted the volume back, I just take the reciprocal again. 1 over this 0.75 would give you the actual size that the balloon is taking up. So just a nice technique of linearizing the graph. You have a little bit of practice with that, but most important here is the graph is a visual way of representing the data. It helps you track the pattern, especially helps you interpolate where you actually didn't take readings, even maybe extrapolating beyond your readings as well. All right? So I'm going to hold it off from there, and then tomorrow we'll come back and take a look at sig figs. Thanks, guys.